Okay, hi guys. So in this lecture we'll be talking about Lucas reagent. So let me write down the heading first. Lucas reagent. Okay. So in Lucas reagent we have the Lucas reagent is nothing but concentrated HCl and ZnCl2. Okay. So this is used for actually test for alcohol, and we'll just see how in just a few seconds. Okay. So let's say we have a reaction something like this. We have ROH and it is in the presence of HCl and ZnCl2. It will get itself converted into R plus and Cl minus, and then RCl bond would be there, and this would be the redetermining step, and this in case would be acting as base. Okay. So actually why do we need the presence of ZnCl2? The only reason is because when HCl should react with ZnCl2, it gets more acidic. And hence when it gets more acidic, its reactivity increases. Hence reactivity increases. Okay. So let's say another example, we have something like -3 degree alcohol, and we are passing this in a Lucas reagent, and we'll get something like the turbidity of halide appear immediately, means this RCl, the turbidity of RCl we are talking about. So the turbidity appears immediately. Okay. In the third example, we have a secondary alcohol, and again we are passing this in Lucas reagent. So the turbidity takes 5 to 10 minutes, and if we have 1 degree alcohol and we again pass it in Lucas reagent, it will take 30 minutes, and it may also need heating. Okay. But if we take something like a phenol and pass it with Lucas reagent, then no reaction is seen to happen. Okay. So hence it's a test of, or Lucas reagent can be used for separating a mixture of phenol and alcohol. Okay. So we can differentiate. And by the way, why this time this type of time limits are seen? Because you know that 3 degree alcohol will be more reactive to Lucas reagent because of the formation of more stable carbocation, and 2 degree would be less stable than 3 degree, and 1 degree be more less stable than 2 degree. Hence it is showing these time limits. Okay. So we can differentiate. Alcohol and phenol by this test. Okay. And suppose we have another example in which we have something like this passing through Lucas reagent, which is HCl ZnCl2. We will have something like this via SN1 mechanism. Why? Because the formation of carbocation will take place here, and it would get stabilized by the conjugation of by the conjugate pi bond. Okay, another example, we have something like this. We pass it with ETO minus. Okay, now we'll get a partial negative charge on this carbon because it will act as a base here. So it would be something like CH, OET, CH2 and Br. Okay, let me put the heat symbol also here. So it will take place in the form of even CB reaction. Okay, oh, this would be, by the way, negative charge here. Okay, we have a negative charge here and ETOH would be formed. And now as you can see, for the even CB to continue, it must have a weak or a good leaving group, but Br in this case is a weak leaving group. Now if we pass it through ETOD, what will happen is it will take on D plus and it will form something like CH, D and CH2 Br. Okay, and if we react this with I mean this compound only with again what we call as having a E2 mechanism wherein we have something like alcoholic KOH and we are heating it. So what will happen is obviously the pi bond formation will take place, and this is the alpha hydrogen. We'll have something like okay with minus HBr. Okay, so please remember this example, because in this case a partial even CB reaction took place in which the carbanion was formed at more stable carbon position, which could be involved with phenylketones for the resonance, and then instead as the Br was weak leaving group, we actually passed it in ETOD. So we had something like this compound, and then we passed it into alcoholic KOH. So we had E2 reaction, and finally this product was formed. This was just an example. We didn't have a problem statement. I just wanted to show how these things are in case of complex reaction mechanisms or nested reaction mechanisms. Okay, so next example is we have something like this, and we want to compare the stability of this with obviously this. So which is more stable, this one or this one? So if we compare the stability order here, that in the obviously both have 6 alpha hydrogen and both of 6 alpha hydrogen, so we need to compare the stability based on their structure of hyperconjugation. Okay, suppose here we have, this is the alpha hydrogen, so this is getting removed, so we have something like this. C negative comes here, and we have something like this structure, and in its hyperconjugation we will have something like Okay, I just remove the alpha hydrogen here and give the negative charge here, and then again we will have something like this, right? So two reasons are here. First reason is how many alpha we need to compare the stability of this intermediate carbon ions to compare the stability of these two. So if we count the number of alpha hydrogen, or we need to compare the stability of this, obviously let's say this is compound N and let's say this is compound B. So the number of alpha hydrogen of compound A is more than the number of alpha hydrogen of compound B, that is for sure, right? Okay, this alkene has more number of alpha hydrogen than the counterpart. And second point is the stability of carbon ion. In this carbon ion, if you can see, it is a 2-degree carbon ion. Okay, in this carbon ion, if you see, it's a 1-degree carbon ion. Hence the stability of carbon ion also in A is more than B. Hence A's intermediate is more stable than B's intermediate. Hence I beg your pardon, number of alpha hydrogen in A, B was more than A. Sorry, B was more than A, and obviously stability of carbon ion, the one for 1-degree carbon ion, it would be more stability as it is having more number of less number of plus I groups attached to itself. Hence B would be more stable than A. Number of alpha hydrogen also in B is more than A, right? So hence the stability of 2-methyl propene is more than trans 2-butene. Okay, this is a good example. This was asked in some previous year papers as well. Okay, so just remember the important point is, if we have a reagent something like in the first step we are giving H plus and CH3OH. Okay, so we'll have, it will show the means catalysis H plus catalyzed reaction in the first step, and the second step if we are again passing it with RCH2OH, then we will have the addition of RCH2OH in that. Okay, so H plus catalyzed in the presence of methyl alcohol, and then we are passing RCH2OH again in that acidic medium only. So we have example something like this. We have this, and we are passing RCH2OH in the second step, and the first step, let me write down the first step first. The first step would be obviously H plus, and second step is this. So in the first step what will happen is alkene will show additional reaction towards H plus and will form a positive charge here. This is our highly stable IIT cation in the intermediate, hence the reaction will go fast in the forward direction. Now what will happen is, again we have RCH2OH, the positive charge will attack on O, or rather O will attack on the positive charge, either way. So we will have something like OCH2R. Okay, so we will have plus obviously H plus, as it was catalyzed in the reaction, it is recouped in the reaction. Okay, so with this we come to an end of this lecture. In the next lecture we will be seeing a reaction of Grignard reagent with acid derivatives. Till then, good luck and goodbye.